The evolution of maintenance is best understood in three distinct generations. In the first generation, industries operated with basic equipment that was often over-designed and built to last. Maintenance was minimal, largely reactive, and centered around fixing things only after they broke. Downtime was tolerated as a normal part of operations, and there was little strategic focus on asset care. The second generation brought about a surge in mechanization, especially post-World War II, where system complexity and production demands increased. This led to the rise of preventive maintenance. Organizations began to adopt time-based intervals for lubrication, inspections, and part replacements. While this reduced some breakdowns, it was inefficient in many cases, as not all components failed based on time. Maintenance costs started rising due to unnecessary interventions. In the third generation, it became clear that failure patterns are far more complex. Many components fail randomly rather than at predictable intervals. This realization led to the development of more intelligent strategies such as predictive maintenance, PDM, condition-based monitoring, CBM, and reliability-centered maintenance, RCM. The focus shifted to understanding failure behavior, consequences, and selecting tasks based on actual risk. Maintenance became a strategic function aimed at optimizing reliability, safety, and cost efficiency rather than simply reacting to failure or relying on time-based schedules. Maintenance today is no longer just about fixing broken equipment, it's about preserving asset function. Reliability-centered maintenance, RCM, supports this shift by providing a structured approach that focuses on what the system needs to do, not just how often it fails. It bridges the gap between maintenance activity and business performance. RCM evaluates equipment based on its operational context, identifying the most effective maintenance strategies to ensure that the asset performs its intended functions reliably and safely. It moves beyond generic preventive maintenance schedules and instead uses failure analysis, risk evaluation, and consequence assessment to design maintenance tasks that are technically appropriate and cost-effective. This approach ensures that maintenance decisions are based on actual system needs and criticality. It avoids both over-maintenance, wasting resources on low-risk components, and under-maintenance, exposing the organization to high-impact failures. RCM turns maintenance from a cost center into a value-generating activity, tightly aligned with operational goals like uptime, safety, and compliance. The foundation of reliability-centered maintenance is a structured analysis built around 7 fundamental questions. These questions ensure that maintenance decisions are based on function, failure behavior, consequences, and task suitability. The first question asks, what are the functions of the asset in its current operating context? This means understanding both the primary and secondary roles the equipment plays in the system. Next, we ask, in what ways can it fail to fulfill those functions? This identifies the functional failures, specific ways in which the equipment might not perform as intended. The third question dives into what causes each failure, exploring the technical or operational failure modes that lead to those functional losses. Fourth, we examine what happens when each failure occurs. These are the failure effects, which describe the immediate and visible outcomes when something goes wrong. Then, we analyze what are the consequences of each failure. This includes safety, environmental, operational, and economic impacts. This step drives risk-based decision-making. The sixth question is, what can be done proactively to prevent or reduce the impact of each failure? This identifies technically feasible and cost-effective maintenance tasks. Finally, we ask, what should be done if no suitable proactive task is found? In such cases, default actions like redesign, run to failure, or procedural controls are considered. Together, these 7 questions create a framework that links system function with customized maintenance actions, ensuring that maintenance is focused, relevant, and risk-driven. Understanding the core definitions within RCM is essential to applying the methodology effectively. It begins with clearly defining the functions of an asset, what it's expected to do under current operating conditions. These include both primary functions, like delivering output, and secondary functions, such as safety or environmental protection. A functional failure occurs when the asset is unable to perform one or more of its intended functions. This might not always mean complete failure. It could be partial or degraded performance, like reduced pressure in a pump or slower conveyor speed. Failure modes are the specific causes of these functional failures. They describe how and why the asset might fail. Examples include bearing wear, contamination, misalignment, or fatigue. These are essential for selecting the right maintenance tasks. Failure effects detail what happens when a failure mode occurs. This includes the visible symptoms, impact on the system, and any associated hazards or disruptions. This information is critical for understanding urgency and response needs. Failure consequences go a step further by assessing the broader impact of the failure on safety, operations, environment, and cost. This consequence evaluation is what drives maintenance prioritization. It helps teams determine which failure modes require proactive attention and which may be acceptable under a run-to-failure approach. Together, these elements form the backbone of RCM analysis, allowing teams to connect equipment behavior to business risk and define intelligent, customized maintenance strategies. Proactive tasks in RCM are actions specifically designed to prevent failures from occurring or to detect them early enough to avoid significant consequences. These tasks are chosen only when they are technically feasible, applicable to the failure mode, and cost-effective based on the consequences of failure. There are 4 main types of proactive tasks. 1. Scheduled restoration involves overhauling or refurbishing a component at set intervals to restore it to a like-new condition. This is used when the item shows predictable wear or degradation over time. 2. Scheduled discard means replacing a component entirely at a predetermined interval, regardless of its current condition. This is appropriate when items have a known useful life and cannot be economically restored. 3. Condition-based tasks are applied when the failure develops over time and is detectable before it leads to functional failure. These include vibration monitoring, infrared thermography, oil analysis, and other non-destructive testing methods. 4. Failure-finding tasks are used for hidden or protective functions that don't reveal failure during normal operation, such as backup systems, alarms, or safety interlocks. These tasks involve regular testing to confirm functionality. Each proactive task must be linked directly to a specific failure mode and be justified in terms of both effectiveness and cost. RCM only recommends a task when it will genuinely reduce risk or extend asset life, ensuring maintenance effort is precise and value-driven. Default actions in RCM are applied when no suitable proactive task exists for a given failure mode. This occurs when the failure is either not technically preventable, not economically justifiable to address proactively, or when its consequences are minimal. Rather than forcing an ineffective or costly task, RCM relies on default actions as logical alternatives. The most common default action is to allow the asset to run to failure, but this is only acceptable when the consequences of failure are low, such as non-critical lighting, backup monitors, or minor components with no operational or safety impact. Another default action is redesign or modification. This is selected when the failure consequence is unacceptable, but no preventive or condition-based maintenance task can address it effectively. In such cases, the solution may involve engineering changes, material upgrades, or reconfiguring the system. Administrative controls are also used as a default action. These include procedural changes, training, signage, or manual checks to manage risk when technical solutions are unavailable or impractical. The key idea is that not all failures can or should be prevented. Instead, RCM focuses on managing risk intelligently by applying default actions only when proactive maintenance is either ineffective or inefficient. This avoids unnecessary maintenance and directs resources where they matter most. The RCM task selection process is a structured, logic-based approach that determines whether a proactive maintenance task should be applied to a specific failure mode. It starts by analyzing each failure mode individually and asking whether a technically feasible task exists that can detect, prevent, or mitigate the failure. If a suitable task is identified, the next step is to assess whether the failure mode has predictable characteristics, meaning it can be identified in time to act. If the failure provides warning signs and those signs can be monitored, a condition-based or scheduled task may be selected. However, technical feasibility alone isn't enough. The process also evaluates whether the task is cost-effective. This involves comparing the cost of performing the task against the potential consequences of the failure. If the task cost outweighs the risk or impact of the failure, it is rejected. For hidden failures, the process considers whether the failure could go undetected until needed, such as with standby systems. If so, a failure-finding task is preferred, assuming it can be executed periodically without excessive burden. When no proactive task meets all 3 criteria, technical feasibility, detectability, and cost-effectiveness, a default action is applied. These include redesign, procedural changes, or run to failure if the consequences are low. This process ensures that every maintenance action is justified, targeted, and relevant. It avoids the trap of over-maintaining low-risk components and instead channels effort toward high-value failure modes that truly affect safety, reliability, and performance. Applying the RCM process involves a structured, team-based analysis of assets, with the goal of identifying the most effective maintenance strategies based on function, failure, and risk. It begins by selecting the systems or components to be analyzed, typically those with the highest criticality based on safety, environmental, or operational impact. A cross-functional team is formed, usually including maintenance personnel, operators, engineers, and reliability specialists. This team brings together the technical knowledge and operational experience necessary to define asset functions, identify failure modes, and assess consequences accurately. The team follows the 7-question framework of RCM, moving step by step through each failure mode to determine whether a proactive task or default action is appropriate. This structured dialogue is often supported by tools such as flowcharts, failure mode templates, and decision logic trees. Accurate asset data, historical failure records, and contextual information are vital to the process. While RCM software can aid in documentation and tracking, the analysis depends heavily on human judgment, operational knowledge, and team consensus. The process is typically piloted on the most critical assets and refined before being scaled across the plant. It may also be applied selectively, depending on time, resources, and asset priority. RCM is not a one-time exercise. It should evolve with operational changes, asset performance, and feedback from the field. By applying RCM, organizations move towards strategic, risk-based maintenance that delivers measurable improvements in reliability, safety, and cost control. RCM achieves far more than simply reducing equipment failures. It transforms maintenance into a strategic function that supports safety, reliability, and operational efficiency. Its core success lies in aligning maintenance actions with the actual needs of the system, based on how equipment fails and the consequences of those failures. One of the key outcomes of RCM is a reduction in unplanned downtime. By targeting high-risk failure modes with the right tasks, organizations can prevent critical breakdowns and ensure greater system availability. This leads to improved production reliability and better use of maintenance resources. RCM also leads to optimized maintenance costs. It eliminates unnecessary preventive tasks that provide little value, replacing them with smarter, consequence-based strategies. By avoiding over-maintenance and under-maintenance, RCM ensures that every task performed delivers a measurable return on investment. Safety and environmental performance also improve, as RCM highlights hidden or high-impact failures that may not be addressed in traditional PM programs. It allows for proactive identification and mitigation of potential hazards. Beyond performance improvements, RCM also promotes organizational alignment. It creates a shared understanding across operations, maintenance, and engineering about what matters, why it matters, and how to manage it. In summary, RCM achieves higher reliability, greater efficiency, improved compliance, and better decision-making, all by ensuring that maintenance strategies are driven by function, failure, and consequence.